see my intro slide.
Yeah. All right. Thank you, everyone, for joining. It is my tremendous pleasure to introduce Tiger Liu for his public thesis defense today. So thank you all for being here, and it's great to do this. So Tiger joined us here in the Yale Department of Astronomy in 2020. He, before that, received his bachelor's degree in astrophysics with a minor in computer science from Caltech earlier that same year. And Tiger's PhD is focused, as you will see, on planetary dynamics with a particular emphasis on computational n-body dynamics as well as tidal dynamics. Over the course of his PhD, Tiger has built up a really impressive array of independent collaborations. So some of his collaborators are here on Zoom. Many collaborators and friends are here in the room, so thank you all for being here. And he has published a range of papers on both developing and applying computational frameworks. He's really developed a deep understanding of numerical methods and planetary dynamics over the course of the past 5 years. And he's accomplished all of this while casually running marathons just about every weekend, it seems. So I'm pretty sure he ran a half marathon yesterday, but that did not slow him down. He's still here.
It didn't feel great.
From the times that I saw, I have never run a single mile that fast. So beyond his scientific work, Tiger's also been a heavily involved community member. He's co-organized Yale's Exoplanets and Stars seminar over the past 2 years, and he's also participated in science outreach and professional development programs on campus, including Science in the News, Astronomy on Tap, Open Labs, and the Warrior Scholar Program. Tiger was recently awarded the AAS Division on Dynamical Astronomy's Raynor L. Duncombe Prize for his work. So congratulations to Tiger. He will be presenting that right after commencement, which feels very timely, given all of his accomplishments over the past few years. Lastly, Tiger wanted me to announce that there will be pizza from Bar right after the defense. At Bar. So that is a bar. That is the name of the bar, is Bar. It's downtown, in case you're not from New Haven. So easy to remember. And it has been such a joy to have Tiger in the department in the past few years and to see him from the very start of his PhD. So I will let him take it away.
Thank you, everyone, for being here. Thank you for that amazing introduction, Milena. Thank you for being here and letting me yap to you all about my science for 90 straight minutes, hopefully not, on this really, really beautiful New Haven day.
You're a different height than Milena is.
Thanks.
Just so we're all on the same page, we have 2 defenses here at Yale. There's one that's private, behind closed doors, where your committee rakes you across the coals, which they've already done. And there's this one, which is kind of just like a victory lap, right? And this is just for all of you guys, and I don't think I can fail this one. Let me know if I can. But, yeah. I want to thank all my collaborators, everyone whose work has also gone into the work of this thesis, as well as some special thanks to some logistical staff. And something that's not on this slide is our very own Josephine Jayworth is running the Zoom room for us. So if you say something on Zoom, she'll say it to me. Yeah, shall we get right into it then? It may come as a surprise to some that a thesis with the title Planets Are Not Points, something I've considered a rather trivial fact since I graduated from kindergarten, apparently suffices these days for a PhD in astrophysics, but I assure you I will make some very strong arguments to back up my thesis. So let's start at the beginning. To oversimplify a century of research into one sentence, we think we know how planets form. We think they formed out of clouds of dust and gas, and they formed into these nice concentric circles. And for the longest time, we had one data point, our solar system. And for our solar system, this picture worked just fine, and everyone's happy. Then in the year 1995, the first exoplanet, or a planet orbiting another star, was discovered. And that instantly took a hammer to this whole framework, because we see a lot of exoplanet systems that do not look like concentric circles, right? We see all sorts of crazy, wacky exoplanet systems. Now, we think that that initial picture is correct. We think that that's actually how planets form. But we still see tons of planets like this, so what gives exactly? Right? Well, if planets formed out of disks and circles, and they end up here, well, they must have moved there, right? So that's what I study. I study planetary motion. Papers are the currency of our field, and these are all the papers that I have written over my 5 years as a PhD student that have contributed to my little corner of the study of planetary motion. There's not enough time here to go into everything in depth. I've just done too much cool science, I'm sorry, but as my advisor Greg Laughlin once said, no one has ever been disappointed by an astronomy talk ending early. So in that spirit, we will focus on just 3 of these papers. And I'm first going to dive into the most fundamental problem in planetary dynamics, the so-called n-body problem. I'm going to tell you what it is, why it's a hard problem, and my development of some tools that help us solve it. That was supposed to happen earlier. All right. It would be remiss of me, before I go on, to not mention the rebound package, and that this is a code package that's designed to study planetary motion and the n-body problem. I remember in my first grant I was writing as a grad student, I wrote this lengthy paragraph about why we were using rebound and what it was, and then Greg took one look and deleted it. He said, explaining what rebound is like explaining what Microsoft Word is. It's like, it is difficult to fully quantify how impactful rebound has been to the exoplanet community. Rebound is open source, which means the code is all public, anyone can contribute. There's no secret branches for collaborators only. You are free to look at the rebound code, and if you think you can do better, go ahead. And yeah, like I said, rebound is designed to solve the n-body problem. The n-body problem is conceptually simple, right? Before I talk about planetary motion, it would be a good idea to define what a planet is, right? And for simplicity, right, let's go ahead and say planet is this. Can you see that? Right there. For simplicity, I want to say that planets are points for now. And what that means specifically is the force on a pair of planets is given completely by this equation. I've been cautioned against putting equations in public talks, but maybe I can get away with this one, right? Because this is a pretty simple equation that we may have seen in high school physics. This is point particle gravity. And it turns out that the n-body problem is, well, we have these forces. Given that, how do these n bodies move under the influence of gravity, given their positions at some future point in time? Now, it turns out, for n equals 2, this is pretty easy. You calculate the forces, work out the math, and an exact analytic solution pops out. And what I mean by exact analytic solution is that there's an equation you can pop a number into and get exactly the right answer right away. Now, I've been cautioned against putting equations in public talks, but maybe I can get away with just one more, because this one's also pretty simple, right? And it turns out that this is the solution to the two-body problem. And what it tells us is that these bodies orbit each other. They just go around in circles, or more accurately, ellipses, elongated circles, right? We've actually known the solution to the n-body problem since the year 1609, the days of Kepler. This equation, with a few others, are the so-called Kepler's laws. If you do something cool in astronomy, you get to put your name on it. So that was the two-body problem. Let's move on to 3 bodies, right? And it turns out all hell breaks loose here, because if you think about it, right, like it's all connected, and if this particle here moves a little closer to this particle, well, the forces on this particle change, and this particle has to move now, but now you have to recalculate the forces on both of these, right? And it's just a nightmare, right? It turns out there is a solution to the n-body problem, the 3-body problem. We can write down an equation that solves this. And it has 10 to the 8 million terms in it, right? And one of you out there is thinking right now, okay, that's not bad. We can put a grad student on it, and it can be their full thesis to write these 10 to the 8 million terms, and it'll take 5 years. And I just want to point out that the number of atoms in the universe is 10 to the 80, so it might be a long PhD thesis. But yeah, there lies the problem, right? We cannot exactly solve the n-body problem. At least I can't solve the n-body problem. So to study planetary motion, we have to find ways to numerically approximate the n-body problem. And here lies the challenge, right? Because while analytic solutions are exact and instant, numerical solutions are inexact and costly, right? To understand why, we have to understand how numerical approximations or numerical integration works. Here's how it works. You take a planet or a body, you calculate all the forces on it, and you assume it moves in a straight line for some period of time. You get a new position, and you do it all over again. You calculate all the forces on this planet, and you do this over and over again, right? And you can see, right, that this will never be perfect. This will never be perfect because the forces are changing instantaneously, right? They're always changing. And you can imagine if this is the true trajectory of your body, you can take smaller time steps, right? And this will get you closer to the true trajectory, but you will never exactly get there, right? Because you can't take an infinitely small time step. And you also realize, right, that the more accurate you get, the more equations you have to compute. The exact analytic solutions have one equation. For the numerical solutions, you have to compute the equation every time step you take. Now this specifically is called the Euler method. You do something cool in astronomy, you get to put your name on it. And this is the first way we figured out how to do this, and this is actually the worst way to do this. We've come up with much better ways to do this in the past, 300 years or so? And we're going to walk through a few of those. So the gold standard today for accuracy in the n-body problem, solving the n-body problem, is called IES-15, developed by Hanno Rhein and Dave Spiegel in 2015. These guys did not get the memo that you can name cool things in astronomy after yourself, right? But IES-15 is the gold standard for accuracy, and my mind is always blown when I see this in the IES-15 paper, because what it's saying is that IES-15 is as accurate as computer hardware allows, right? The accuracy of IES-15 is, the algorithm is not the limiting factor anymore, right? And I think this is really cool, right? Essentially, we have solved the n-body problem with IES-15 to the extent that it can be solved numerically. It's short of someone solving a 10 to the 8 million equation term, right? On the other side of the pendulum, there's the Wisdom-Holman method, developed by Wisdom and Holman in 1991. These guys did get the memo, and it was re-implemented by Hanno Rhein and Dan Tamayo in the year 2015. And this integrator specifically stands for Wisdom-Holman Fast. Right? And Wisdom-Holman Fast, or WH-Fast for short, is an integrator that's super fast, right, but gets you the wrong answer every single time. Well, that doesn't make any sense, right? Like, what's the value in having a quick integrator if you can't trust it? And it actually turns out that Wisdom WH-Fast is actually really, really accurate too. It's just barely a little bit less accurate than IS-15. So you may ask yourself, what's the point in using IS-15? You can be a lot faster and almost as accurate. And it turns out there's actually a third axis to this graph. This is the flexibility axis. And while IS-15 is very flexible, Wisdom-Holman is not flexible at all. And to describe what flexibility means, that means that you can take any system you want, right? You can run IS-15 on it, and it will get you the right answer. You cannot do that for WH-Fast. In fact, you can only do that for WH-Fast for very specific systems. And that specific type of system is actually a very relevant system to planetary dynamics, the so-called planetary n-body problem, where you have a dominant central mass and a lot of little guys surrounding it, right? And if you think about it, this is just like our own solar system, right? The little guys, they care about each other, but not really, right? The main source of force and motion in this system is the interaction between the big boy and each of the little guys, right? And if you just zoom in on a big boy and a little guy, right, what's the motion? Well, Kepler figured that out. It's just a circle, right? It's just an orbit. And so that's the genius of the Wisdom-Holman method. They realized that a lot of time is spent kind of rediscovering Kepler's laws every single time step. And you don't have to. You can assume you know them and just treat everything else as a little prediction to that. So Wisdom-Holman is the gold standard for integration of planetary systems today. You can do or you can integrate planetary systems for billions of years, which is the required timescale you need to actually see their evolution, right? And this has revolutionized the field, but there are some problems with Wisdom-Holman, right? And those problems come from inflexibility. Wisdom-Holman fails when you can't make that assumption of a perfect orbit anymore. And that happens, for example, when two planets get really close to each other. Their gravity dominates. You also can't deal with planets getting really close to their host stars. The planet's moving too fast. This perfect orbit just doesn't really make sense anymore. So that's where this idea of hybrid integrators come in, right? And the top hybrid integrator on the market in the past was called Mercurius. And the idea of hybrid integration is relatively simple. You use Wisdom-Holman when you can, and you switch over to something like IS-15 only when you have to. Right? So if you look at this diagram here, if your planets are all very far away from each other, right, you use Wisdom-Holman to advance your system. If and only if your planets get really close to each other, right, you switch over to IS-15. The problem with Mercurius, right, and Mercurius is great, it's been a great tool for the community, but the problem is that it can't handle close encounters with the central star. You try to do it with Wisdom-Holman and it just completely fails. So we did better, much better. We came out with what is, I believe, to be the best hybrid integrator on the market today. TRACE, which stands for Time Reversible Astrophysical Close Encounters. These guys did not get the memo that you can name something cool in astronomy. So in lieu of that, I really want to thank my roommate, Yasmin Asali here, for actually coming up with the name of this hybrid integrator. Thank you, Yasmin. And yeah, the very first thing you might think of when you see the name is time reversible. What does that mean, right? That's not immediately clear. What it means is that the natural world, many things in the natural world are time reversible. They make sense both forwards and backwards in time. So this is another video taken by my roommate Yasmin. And in this video, I'm dropping a small stuffed bumblebee onto the ground, right? This is not for the thesis, we just do this in the office sometimes. But you can argue the ethics or morality of this video all you want, but what you can't argue is that this makes physical sense, right? The bumblebee starts at rest, Earth's gravity is pulling on it, and it speeds up, right, as it goes down. I'm sure this makes sense, right? We've all dropped a small stuffed bumblebee at some point in our lives. But what might look a little stupid, but also makes sense, right, is if you play this video in reverse, right? Here we go. Yeah, what also makes sense is if you play this video in reverse, right? And while this looks a little sillier, this still makes physical sense, right? The bumblebee starts with a fast velocity, Earth's gravity is pulling on it, and as it reaches my hand, it stops moving, right? And it turns out that the key to fast and active integration is to enforce this time reversibility. And it turns out for doing this for like gravitational forces is relatively simple. They're just time reversible by default. But the tricky thing is you have to make sure your switching is time reversible. When you switch between Wisdom-Holman and something better, you have to make sure that switch is time reversible. What does that mean exactly? This was work done by my collaborator David Hernandez, right here in the audience, in 2023. And what David realized is that there's actually a very simple way to check that the behavior of your integrator forwards in time is the same as backwards. So how you would do this, right? You have to decide that particles are close somehow, right? So let's do this the simplest way. Let's draw a line. Let's say if it's within this line, it's a close encounter. If it's outside, it's not, right? You check before. This is outside the line. Let's integrate with Wisdom-Holman. Right? Next time step, check. It's inside the line. We integrate with IS-15. All good, right? But this has to be the same in reverse, right? So if you flip the sign of time and you look at how the system behaves in the reverse time direction, well, the first reverse step is all good, right? But the second reverse step, now look, you're inside this line to begin with, and you're going to integrate with IS-15 now. So that means that the behavior of your integrator is different forward and backwards in time. And the great genius of Hernandez and Dane in 2023 was realizing that you can do this by not just checking your particle before your time step. You check it both before and after. So if you look at this time step here, we would integrate with Wisdom-Holman, check again. We realize, oh no, we shouldn't have done that. We reject the step, and we integrate with IS-15. Now, in practice, right, only like 1% of steps are actually rejected, but it turns out that rejecting and redoing just this tiny number of steps is enough to get you huge speed and accuracy bonuses. Here's one example. This is a system that Mercurius does well, and Wisdom-Holman doesn't, right, with close encounters. And we'll see that Wisdom-Holman completely fails instantly, but TRACE, our new integrator, does about as well as Mercurius does from an accuracy standpoint. But then you look at the run times, and TRACE is over 10 times faster. It's an order of magnitude faster, right? I want to show one more example, but to do that, I have to introduce this concept of chaos first. And what chaos is extremely sensitive dependence to initial conditions. These are 3 sets of double pendulums, so 2 pendulums connected to each other, and we've started each one just a tiny bit separated in initial conditions. You see that these tiny initial differences propagate quickly, and eventually they're doing just completely wild things that you can't, it's impossible to compare, right? Many astrophysical systems are also chaotic in this way. So that means if you want to analyze an astrophysical system, you can't just compare one simulation to another. You have to compare populations of simulations and compare those large-scale results. One such process is planet-planet scattering. This is believed to happen in a lot of primordial planetary systems. You pack a lot of mass into a small area, right? It turns out these planets are going to interact with each other very strongly gravitationally. And this is going to induce instability. Planets may be thrown out of this system. Planets may be thrown into the central star. Right? And it turns out that this process is highly chaotic. You move one of the planets by less than 5 inches, right, in just one direction, just one of the planets, You can get wildly different results. So we actually ran this system 500 times, testing Mercurius, Trace, and IAS-15. The first thing you see is Mercurius gets things instantly completely wrong, right? This is a simple statistic we plotted. It's just the number of surviving planets at the end of the simulation. And Mercurius is telling us we should expect a lot more one-planet systems. And this is because every time a planet gets too close to its host star, Mercurius does not even try to handle it, right? It just throws it out instantly. Trace, our integrator, does just as well on a population level as IAS-15. You can't tell the difference, right? But let's look at the runtime now. And Trace is 20 times faster than IAS-15. So we are getting the same results as the gold standard for accuracy in this field at 20 times faster. So I'm not claiming to have solved the n-body problem here, far from it. But what we have done with Trace, I think, is pretty cool. We've developed a tool that is going to be the go-to for this very specific but extremely relevant special case of the n-body problem. Unfortunately for us, the n-body problem is not quite all there is, right? And the n-body problem is not quite all there is because it turns out planets are not points, right? Let's go back to this. I don't think planets look like this, in my opinion. I think planets look more like this. Would you guys agree? Closer? Yeah. Planets have extent, right? They have some size to them. They also spin. And if a planet spins, it's going to be slightly rotationally flattened. And maybe most importantly, they are affected by tides, right? And I'll go deep into tides in a little bit, but this is something that meaningfully changes the orbit of your system, right? Now, I've been cautioned a few times about putting equations in public talks, and maybe I can get away with one more, because this one's also pretty simple. Oh, that's ugly, right? Yeah. Yeah, and if you think about it, right, how are we supposed to solve this? We could barely solve just that, right? That was a very famous hard problem. Now we have to deal with all this. What I have done, I don't expect us to gain any deep insights from looking at these equations, but what I will do is, not that, okay, well, some of these things were supposed to be red.
They're red on here.
Okay, well,
Sorry.
well, some of these quantities are supposed to be red. They'll pop up later. And those red quantities are the quantities associated with the structure of the planet, right? Things like the radius, right? Things like the density, things like the degree of central concentration, right? But yeah, the n-body problem with just points is a famous unsolved problem. It'd be a real task, right, to take these equations, these incredibly crispy equations, and put them in an open source, publicly available, easy to use package for the community at large. So we took these crispy equations and we put them into an open source, publicly available, easy to use code package for the community at large to use. This is the tide spin package, which is in Rebound. And this is kind of the foundation of my thesis. This is a project that every other project in my thesis has used in some way or form. But before I go into that, I showed you guys a bunch of equations, but hopefully I can shed some light on what they actually mean. I said the most important thing was in going from points to extended bodies was tides. And when you think of tides, you maybe think of the ocean rising and falling, but why does that happen? That happens because of imbalance, and that imbalance happens because planets are not points. If your planet is not a point, and you have something acting gravitationally on it, let's say a moon, for example, the gravitational force on the close side of the planet is going to be greater than the gravitational force on the far side of the planet. Planets are not perfect titanium balls, right? They can stretch and give, they can, deform a little. So it turns out that this creates a tidal bulge, right? And that bulge wants to point towards the moon, right? Because that's the direction gravity's pulling you. But planets move, right? I study planetary motion, and planets move. So we've got to keep in mind that this moon is also moving, right? And the tidal bulge then wants to follow the motion of this moon, right? And the problem is that while planets are not titanium balls, they're also not Play-Doh. They react and deform in response to perturbations, but they don't do it instantaneously, right? So if we take a snapshot of the tidal bulge and your perturber at this one point in time, you can draw a line between your perturber and the center of your body, and you can draw a line pointing in the direction of your tidal bulge. And the problem is, right, that because the bulge does not react instantaneously, it will always be slightly misaligned. with the line of centers connecting your moon and your body. And in this case, right, the bulge is actually going to pull back on the moon. It's going to pull back on the moon, and this will drain energy from the orbit, right? So this is how tides affect orbits, right? They do two things. They draw you closer in, but one thing they can also do is go from a relatively eccentric orbit, a relatively elliptical orbit, to a more circular one. That's going to be important later on. I said that this was the foundation of my thesis. These are all the papers that I have written that have used this framework in some way or form. Again, I can't go into all of them. I've just done too much full science. I'm sorry, but I do want to focus on this project here, which is a project I'm really excited about, and this is what's going to be the foundation of most of my postdoc work. And what this is another redefinition of a planet, because I'm going to contend that this is actually the most accurate depiction of a planet we have so far. Planets have structure, yes, but in the previous stage, I assumed that that structure was fixed, right? In reality, planets are incredible dynamic things, right? Planets lose radius, planets can gain mass, planets can change over time very, very meaningfully. And it's interesting because this is the field of planetary interiors now we're talking, planetary structure. And planetary structure and planetary motion are two of the great pillars of planetary science that have advanced in lockstep but never really talked to each other. This, and if we go back to our equations, right, what this means is all of the quantities associated with planetary structure, things like the radius, things like the love number, which describe how centrally dense it is, all of these will now have a time dependence on it. And the specific time dependence of all these structure quantities depends on your interior structure model. So you can see how this gets incredibly complicated, incredibly quickly, right? We were worried about just that. Now we have all this. This is arguably the oldest question in exoplanet science, actually. Because there are these class of planets called hot Jupiters, and a hot Jupiter was actually the very first planet to be discovered. And when these hot Jupiters were discovered, it was found that they were too puffy, right? They were too large. They were large in a way that interior structure models could not explain. So this is a plot by my advisor, Greg Laughlin. What we're plotting on the x-axis is temperature. And this is kind of a proxy for how close a planet is to its host star. And on the y-axis, this is the so-called radius anomaly. And this is how much bigger the planet is from what you'd expect, right, from standard structure models. And we can see a trend, right, that the hotter your planet is, the more puffy it is. So this is actually still a very famous unsolved problem, so we're not going to claim we've solved it. But we think we have some ideas for what's going on. And here's one hypothesis. Remember when I said that the tidal bulge really wants to be aligned with the line of centers connecting the perturber with your planet, but it's not, right? Well, it's always trying to be, and that causes friction in your planet. Friction causes heat. Your planet's interior is going to heat up, right? And if your planet's interior heats up, just like a hot air balloon, its envelope, its atmosphere is going to expand also. This is a plot from one of my most recent papers, but the data in this plot comes from Sarah Milholland's 2020 paper. And what Sarah has done here is she has injected luminosity, she's run interior structure models of planets, and she has injected heat into each of these planets' cores. And she's tested how much these planets puff up. So we have how much heat we're putting in on the x-axis, and we have how big the planet puffs up on the y-axis. And we can see that roughly, a planet with 3 Earth radiuses can puff up to more than twice that with a very reasonable amount of heat. So this is a really profound effect, right? And I'm hoping to convince you that this is actually very subtly important to how planets move. And I'm going to explain that with a detailed case study of my favorite planetary system, which is the HAPP-11 system. HAPP-11 is a fascinating system because remember when I said that planets are supposed to form in concentric circles? Every single aspect of the HAPP-11 system is not a concentric circle. There are 2 planets, both of them are non-circular, both of them are not concentric, both of them are misaligned, right? This paper itself, in this paper we did a deep dive into every aspect of the HAPP-11 system. I don't have time to go into all of that today, So I want to focus on planet B, and planet B is really the interesting one in this system for a couple of reasons. Planet B orbits the star perpendicular. It's very close. It orbits its star with an orbital period of 4 days. For reference, Mercury orbits with an orbital period of 80 days. So this is really, really close. And this, coupled with the fact that the planet is actually on a non-circular orbit, is very slightly eccentric. That's very interesting, because remember when I said that tides circularize your orbit? Tides are much more efficient when you are very close to your host star. Right? So that close to your host star, you would expect this planet to be long circularized. So this is a question that merits explanation. This is our hypothesis. Right? We proposed that Happy 11, actually Happy 11b, this is the inner planet, formed slightly further out than we see it today, where tides were less efficient, right? And then something moved it inwards, right? So it moved inwards and it was able to keep a little bit of that residual eccentricity. The specific mechanism at work here is the so-called von Zeipel-Leadoff-Kozai effect, or the ZLK effect for short. And this is a really fascinating dynamical effect that does a number of really interesting things for planetary systems. But I'm going to focus on just one aspect of the ZLK effect. This happens in systems with one big central guy, a little guy orbiting pretty close, and a slightly bigger boy that's orbiting both of them, right? In systems like this, if you start your little guy on a concentric, if you start your little guy on a circular orbit, it turns out that perturbations from the bigger guy outside are going to force your little guy to become more and more eccentric, right? And the idea here is when you pass your star every time on this eccentric orbit, energy is drained from your orbit and you get closer in. That's how you bring your planet closer in to its present day position. So the idea behind this project was actually pretty simple. We were just going to do a few of these simulations. It was just going to take 2 weeks. It'd be a quick and easy paper, right? But something bad kept happening to Happy 11b. This kept happening to Happy 11b. That's not good. Here's our planet. Let's try again. That's not good either. We are losing our planet every single time. And we are losing our planet every single time because it turns out that there's this zone around your central host star where these tidal forces are so strong that they actually rip your planet apart, right? Planets cannot survive in this region. And in all of our simulations, Happy 11b was entering this region. And we were losing all of our planets. And to understand why, we have to understand a little bit more about how the ZLK effect actually works. It turns out that if you go through and do all the math, you work it out, and the reason the orbit becomes more eccentric and hence closer to its host star is because of orbital precession on the little guy due to the big guy. Precession is if your orbit is not circular, you can think of it as pointing in a certain direction, right? And the orbit will slowly move over time, right? I've been cautioned against putting equations in public talks, but if I can get away with just one more, what this equation here is, we can actually write down exactly what that precession rate is. And it turns out that this precession rate here, due to the outer guy, right, depends completely, basically, on the orbital architecture of the system, where the outer guy orbits, how big it is, etc. Now, it would behoove us to remember that planets are not points, so something else is happening here also, and that something else is tides. Every time you come close to your host star, the close approach on an eccentric orbit, tides will drain energy from your orbit, and your orbit will shrink closer in. And this is interesting, right? Because it turns out that tides also have a small precession effect. They also cause the orbit of the planet to start pointing in different directions over time. Now, again, I've been cautioned against putting equations in public talks, but if I can just get away, this is the last one, I swear, this is the last equation, we can actually write down exactly what this precession rate is too. And I just want to draw your attention to this it was supposed to be highlighted in red, but this extremely strong dependence on A sub B down here, which is the southern major axis of the planet, aka how far away it is from the host star. And what that means is, if you're really close to your host star, you don't care at all about tidal precession. If you're really far, you don't care about tidal precession. If you're really close in, you start caring a lot, right? And this is important because this is actually how you kill the ZLK effect. This is how you stop your orbit from getting very, very eccentric. You stop the ZLK effect when the precession due to your outer guy is no longer the dominant source of precession in your system, when something like tides take over, right? And it turns out that this depends basically completely on how close your little guy is to your big boy. So armed with these two equations, we can understand what's going on now. We're going to animate the system without the planet itself, because I couldn't figure out how to move it. And let's compare, let's think about what's happening, right? There's a precession force due to the outer guy, somewhere far out there. And that is going to cause the orbit to become more and more eccentric, right? At the same time, there's a tidal precession also. And this tidal precession starts out very weak, right? Because you're pretty far away from your host star to begin with. And the closer you get, the more important your tidal precession is, right? And what's happening in every single one of our systems is this tidal precession is not growing fast enough. You are not killing the ZLK effect quick enough to avoid your planet being ripped apart. So we did come up with a solution to this problem. Happy 11b is alive and well. We came up with a solution. And to understand the solution, we have to take a closer look at the equation for tidal precession. Now, before this, I really pointed out the strong dependence on semi-major axis, A sub b there. But it turns out that if you're an astute observer, you'll realize there's also an incredibly strong dependence on R sub b that's also highlighted in red, supposedly. This is the radius of the planet, right? And it turns out that the tidal precession rate depends on how much you puff up your little guy. This is our idea, right? You get onto an eccentric orbit. That makes you get more tidal heating because you pass close to the star. Remember, you get more tidal heating, your envelope puffs up more. That induces more precession. And that, hopefully, if you look at two systems, one where you include the effects of your planet puffing up, and one where you don't, hopefully what happens is if you include the effects of your planet puffing up, your precession due to tides will grow fast enough so you avoid getting tidally disrupted. That was the hope, and that's what we did. We implemented these models from Sarah Milholland's 2020 paper into our n-body simulations. We took the simulation, we calculated the tidal luminosity at any given point, and we puffed up our planet to that size. And then we ran our simulations. And they worked, right? They worked. They worked because, exactly what I said, the tidal precession goes fast enough. And then when we ran our simulations, we see that while our planet was previously getting destroyed, our new planets that are now puffing up as they get closer to the host stars are surviving. They're still getting very eccentric, they're still passing very close to their host stars, but it turns out that it works out just enough that your planets are barely avoiding destruction. So this is actually able to explain every observed aspect of the Happy 11 system. And what I think is really cool, actually, is not just that, but you can only explain this if you include radius inflation, right? We ran a set of simulations with and without radius inflation, and in every simulation without radius inflation, where planets just had structure but not evolving structure, your planet is basically destroyed every single time. Whereas the simulations that included radius evolution, you get basically the correct answer. And I actually think that I'm really excited about this idea because I think this solves a really big problem in planetary science right now. The very first planet ever discovered was called 51 Pegasi b, right? And this is a hot Jupiter, a giant planet that orbits very close to its host star. And these planets shouldn't exist because there's just not enough stuff that close to its host star to form it. So we actually think they formed further out and migrated inward somewhere, maybe through the ZLK effect, like I just mentioned. And the community has almost arrived at a consensus to this. We almost think this is how it works. But we don't fully believe this is how it works because of the reason I just talked about, because in all simulations of this migration process, too many hot Jupiters are getting destroyed. And I'm really excited because I think that this new idea of incorporating structure and the motion evolution of your system can save a lot of these hot Jupiters from a fiery death. So, that was my thesis. I'm going to leave up my main points here, but I do want to just talk about one takeaway, which is that the natural world is a very complex and beautiful thing, right? That's far beyond any of our abilities to completely explain. So we have to build simplified models and try to draw insights from them. An economist cannot predict cannot predict the behavior of every single person in the country, right? So they have to make models, and that can still make you a lot of money. A biologist cannot understand every single neuron, but we still have developed a deep understanding of the human brain because of simplified models. In astronomy, right, we cannot possibly model the effect of every peak and valley on a planet's surface on motion of the planet. So that's why we deal with points, right? The general idea is you start with a model that's as simple as possible, and you increase the complexity of the model when the data throws you a bone, right? When the data gives you something that you can't explain with your simplified model. And I'm going to contend that the quality, the quantity, and the strangeness of astronomical data today warrants these nuanced, detailed models. Cool, that was the science. This is the fun part. All right, shall we begin? This is Greg Laughlin. The book starts and stops with Greg. Greg was my advisor for my first 4 years of grad school. He's recently retired, so no longer, but Greg made me the scientist I am today. Greg is the reason I came to Yale, partially because he's also a huge writing nerd. He was faster than me for a little bit, which I didn't like. But no, mostly because I was really struck by his creativity and his ability to answer questions that people wouldn't even ask, right? Greg, I think, would call his creativity his greatest strength as a scientist, and I'd really like to think that's one of mine too. And the one thing I really appreciate about Greg Laughlin is his loyalty. And what I mean by that is I've never, ever doubted that what Greg was saying behind me, was saying to me, saying about me behind closed doors to other senior astronomers and people who had the power to shape my future. And I know that no matter how many years removed from astronomy he becomes, that he will be my and every single other Greg Laughlin student's biggest advocate. So thank you, Greg. Thank you for always being in my corner, and thank you for making me the scientist that I am today. It's been a pleasure. Milena Rice. Where to begin with Milena Rice? Well, they say a picture is worth 1,000 words. So before I go on, I think this is technically, Milena has only been my advisor for a few months, but really she's been an incredible mentor for me ever since we were grad students, right here together at Yale. She was the superstar senior grad student, getting tenure track and Forbes 30 under 30 offers back then. And these days, it turns out she's a pretty darn good professor of astronomy. Through it all, she has been my academic role model. She has always put my success first, and I've learned so much about how to be a successful scientist. Milena Rice also happens to be one of my best friends in the world, and it is really such an amazing and special thing to be able to call my advisor one of my closest friends. I think more people should do it, honestly. It makes things really easy. We'll have this 20-minute quick research chat that'll turn into a 90-minute gossip session that'll seed the ideas of 5 new papers somehow. And I'm really so thankful for Professor Rice, my amazing research advisor, but I didn't need that. What I really needed was someone who I could instantly text with any news, someone who celebrated my wins just like her. And I needed someone who was going to cut a Zoom meeting short, to hunt me down for a big hug the moment I told her I got offered the postdoc that I was going to accept. And when Milena did that, I think her smile was bigger than mine. And if you're wondering what that looks like, it looks a lot like the smile on her face right now. So, Milena, I don't know if I have the words to tell you how grateful I am. I don't think there are words, but I hope you know. Objectively speaking, a PhD is never worth it, right? From a stability it's true, right? From a stability or a financial or a work-life balance standpoint, people with our skill set can always find something better, right? So you don't do it for that. You do it for the intangible things. You do it because it's a fundamentally beautiful thing to wake up every day and chase your dreams with people next to you who are just as passionate as you are. So you have to decide, right? You have to decide if those things make it worth it to you. And for me, it is, and there's no question about it. And when I think about who made it worth it, all the long nights, the uncertainty, all the ups and all the downs, there's one person that stands out above the rest. So thank you, Milena Rice. I'm truly honored for the chance to be your first PhD student. It's pretty crazy how there's 8 billion people in the world, and I'm lucky enough to have your name on the first page of my dissertation. I can genuinely say this without an ounce of exaggeration or embellishment, but Konstantin Batygin changed the trajectory of my life. Caltech is not an easy place to go to grad school, or go to undergrad, and I didn't handle it perfectly. By the end of my 4th year, I was beset with crippling imposter syndrome, and I was super burned out. It's hard not to, right? I was surrounded by some of the most brilliant people in the world, and I was just barely getting by. And that's why I'll remember this conversation I had with Konstantin for the rest of my life, because he was the one who pushed me to apply to grad school. I remember he offered, I didn't even ask, he offered to write my rec letter. And I know that rec letter is why I got into Yale. I know it wasn't my research accomplishments, because honestly, I'm serious, this is not a joke, I didn't have any. And grad students are a big risk, right? Because they're a big commitment. If you have a software engineer that doesn't work out, you fire them. But if you have a grad student that doesn't work out, you're stuck with them for 5 years. Sorry. So it was a big risk, right? Both on Greg's part and on Konstantin's part for advocating for me. And at the time, right, I didn't understand why. I was a late bloomer in grad school. I didn't think I was worth it for the longest time. I'm starting to think I'm worth it now. So thank you, Konstantin, for taking a chance on me. This PhD journey does not happen without you. Science is an incremental thing, right? You look up at the mountain that's been built up by all the brilliant people that have come before you, and you pick a ledge on that mountain that looks particularly interesting to build your own research on. Well, Sarah Milholland's work was my ledge, and almost everything I've said today rests on the foundation built by her work. I remember my first ever conference, Exoplanets 4, or Exo4 for short. I was this wide-eyed second-year grad student, and the only reason I went was because I wanted to talk to Sarah. And of course I was terrified, right? Because this is Sarah Milholland we're talking about. This is Sarah Milholland, whose name has already come up several times in this talk. This is Sarah Milholland, the superstar new faculty from MIT. The Galileo to my Newton, if I may be so bold. But I did end up mustering the courage to talk to her, right? And I did, and that was one of the best decisions of my life, because today, and ever since then, Sarah Milholland has been one of the most impactful and important people in my career. And I think back now to how terrified I was at Exo4, and it all seems so silly now, because this is Sarah Milholland we're talking about. This is Sarah, who's one of the nicest and most genuine people in the world, who has ended up being my longtime collaborator and friend, and who has always been in my corner. Going back to postdocs for just 1 second, it's really stressful, right? You see all these incredibly talented people competing for all the same positions you are, and you know, it's a lot to get through, but I knew I had an ace up my sleeve that they didn't. Because you know, MIT fellowships get 400 applicants for 2 spots. I know that Sarah's going to war for me in those committee meetings. You know, some guy on the market has 20 first author papers. I know his letters aren't as good as the ones Sarah's writing for me. And these are never things I had to wonder, right, or hope for. These are things that I just knew. So thank you, Sarah, for being my academic big sister. We have a lot more science to do together. So Gongjie Li taught me everything I knew, and I sometimes affectionately call my 3rd and 4th years my floundering phase. And this was when I felt like I bit off a little more than I could chew. When I was juggling 10 balls in the air, you know, couldn't put any down because postdoc season was looming, and I felt like I had to just like get things out. And that's when Gongjie came into my corner, and that was really the perfect time, because that's when I really needed someone like Gongjie, someone with endless patience and kindness, and looked past all the chaos and saw some potential. I can't count the number of times when we finish our weekly Zoom meetings, in like 10 minutes because I had nothing to report. And every time Gongzhe would sign off with a smile on her face and a cheerful word of encouragement for the next week. And eventually I started catching up with those balls, right? And this paper here, Liu on Li 2025A, this is the paper that got me my postdocs. This is the paper that I'm proudest of, the paper that I feel best represents me as a scientist. So, and Gongzhe Li was my primary research advisor for this paper. So, Gongzhe, thank you for sticking with me. Thank you for your patience, your faith, and helping me find my footing when I really needed it the most. Rosemary Marling and Doug Lin are titans of the field. They're inarguably two of the greatest astronomers alive. They're my heroes, and they still are my heroes. But somewhere along the way, I got lucky enough to call them my mentors, friends, and collaborators. And more than anyone on this list, they didn't need to take me under their wing. Their legacies, they didn't need another successful student. Their legacies would have been secure if they stopped publishing 20 years ago, right? No, they did it because, as Rosemary once told me, they are scientists who are driven by curiosity, fascination, and the deep belief. And working with these two, seeing how they think, seeing their love for the science, for science's sake, it's hard not to feel the same. So, thank you, Rosemary and Doug. It has been a rare and humbling privilege to learn from you both. Always be your heroes. I really hope you're not tired of hearing the word rebound yet, because I do need to talk some more about it. Rebound was my personal introduction to exoplanets back in Konstantin Betigna's class in my third year of undergrad. And rebound's a very easy package to use. We take a lot of pride in that. But it turns out you do still have to read some documentation and read some papers to get started. And that means that the names Ryan, Tamayo, and Hernandez were everywhere in my formative years as an astronomer. So it's really surreal then to see my name today where their names are written. Today, I am the number 5 contributor to the rebound package, if you count by code lines. And each of these 3 has been so deeply pivotal to my career. Hano wrote letters for me for every position I had success in this postdoc cycle. David here was my direct research supervisor for the TRACE project I opened this talk on. And Dan, by the way, was the other person I was terrified to meet at Exo 4. And if you know Dan Tamayo, you know what a ridiculous statement that is. Dan served as the external reader on my dissertation committee. So I'm really, really proud to have contributed to this amazing code. It feels like I'm part of something bigger than myself. And maybe someday there'll be another budding undergrad who will look at my name in the rebound code and think the same things I did. To the senior astronomers I've met over the past 5 years, you probably don't realize how much your kindness has meant to me. Sharing my research in front of people I admire was always really terrifying. And I know one of the people on this list, when I told them they were on my acknowledgements, said, I don't feel like I helped very much. And I say, no, that's a ridiculous statement. Because every single person on this list, when I visited their institutions, went out of their way to make me feel welcome, seen, and at home. I really want to thank Faye Dai and Sminar Neos, who went above and beyond for me. University of Hawaii and UCLA have both really felt like home both of the times I've visited, and that's due to you guys. Their belief in me as a scientist and a person has carried me through this past year. And it was actually Faye, in fact, who first convinced me to apply to postdocs this year. Belief is a contagious thing, and his belief in me made me believe that I could also do it. Yale astronomy. Guys, I say this a lot, but I think we got really lucky, you know? I don't know if it's normal for a department to be this happy, right? For your colleagues to not just be friendly, but for these people to be people you'll be lifelong friends with. I've gone on and on about my senior mentors, and you know, I have endless gratitude for them, but these people here, these are the people who are in the trenches. You're down in the trenches with every day. They're the ones who see all the memory leaks. They're the ones who see the breakdowns, all the tears, all the little moments that go into a really great work of science. And it turns out that when the people in the trenches bring a smile to your face every single day, the trenches aren't such a bad place to be. So there were so many little lifelines in this department that I don't have time to go fully into. But I do want to give a special shout out to Yasmin Asli, my roommate, Sebastian Monson, and Konstantin Gerlig. So here's a really cute picture they took where they have the audacity to go to the winter ball without me. And yeah, thank you guys for being my best friends. Thank you for all the Jitterbus friends. Thank you for all the check-ins that I never had to ask for. Thank you for your willingness to play Mario Kart with me, even when it was utterly humiliating for everyone except me. Thank you for all the little moments, the two-way streets of friendship. Thank you for all the little moments that really seemed so inconsequential in the moment, but looking back, I mean everything, right? What a privilege it was to matter to you guys. Astronomers are pretty awkward, as it turns out. And unfortunately for us, it's a really small field. So networking is pretty important, and that means you have to talk to people, right? But luckily for us, the current crop of junior exoplanet astronomers is pretty awesome. I feel really fortunate to have the chance to have gotten to know so many of you. This is a field that is filled with so many brilliant, kind, and genuinely good people. I'm especially grateful to my friends who, on all my visits to their institutions, have gone out of their way to make me feel welcome at home. People like Nick at University of Hawaii, people like Ben at Columbia, right? The future is really bright for exoplanet scientists, I think. And in the not so distant future, I know that many of your students will be talking about you guys in the same way that I've talked about my research mentors. I want to give a very special thank out to Yubo Su, my very first astronomy friend in grad school. At Exo 5, I was way too shy to talk to anyone, and I failed miserably in my goal of just making one friend. Luckily for me, Yubo thought I was pretty cool, and he actually talked to me, and the rest is history. Yubo, did recently almost forget to cite me, so that position as best astronomy friend is a little shaky for anyone who wants to slide in. But conferences get exponentially easier, right, the more people you meet. And I know quite a few people at this point, but it's still nerve-wracking sometimes, and it's very comforting to know that no matter what waits on the other side of an airplane ride to a conference, at least Yubo will be part of it. I also want to thank Ben Casses, who's my oldest friend in astronomy, back to those Caltech days that we were wee lads together in, right? And look at us today. Look at all these papers. If the quantity of papers is the goal, right? And let's be real, when is it ever not the goal? I think we're doing just fine. And finally, I'd like to talk about Nina Liu, who's also here in the audience, the undergrad that Melaine and I have mentored over the past couple of years. It's been really amazing to see Nina's growth from a budding novice to, I really say this with complete and genuine honesty, a better researcher than I was until my 4th year of grad school. I really mean that. I know Nina will be on the grad school market next year. She is smart, self-motivated, and an absolute joy to work with. I know there are some senior astronomers in the audience today, so if you want your department to suck, I highly recommend passing up Nina's. You guys know that I like running? I bet that's new and novel information, not in his intro, I guess. But maybe it's more accurate to say that I love running with friends. And over these past 5 years, those friends were the New Haven Roadrunners, many of whom are here today. Thanks for showing up, guys. New Haven didn't truly feel like home until I was a part of NHRR. Running is a really deep and meaningful thing to me. It's something I could probably give an even longer dissertation talk on. But for now, I just want to say how fortunate I was to have these amazing friends to share it with. And honestly, the people on this slide today, right here, don't feel like friends. They feel like family. Lizzie Millendale Perkins and Aziza Chigatayeva, did I say that right? They're like the sisters I've ever had. And they were there for me. They were there for me for some of my toughest moments and darkest times this year, in different ways. But and our very own Josephine Jayworth, who is our club president, who keeps me on a very tight leash. If any of my collaborators out there have ever been disappointed in my productivity, I think 5% of it rests on Jim. That's fair, right? 5%? Sure. Yeah, we'll call it that. Nah, despite my unrelenting bullying, Josie is a very dear friend, and it makes me really happy to see the New Haven Roadrunners balloon from 50 to 400 members today. Feels like something we built together. You know, friends are forever, right? Whether they're on your doorstep or 1,000 miles away. I'm lucky enough to have some really wonderful people in my life whom I know will be friends with for the rest of my life. Every single person on this slide is a young professional living a hectic, chaotic life. But in the rare moments we see each other, it reminds me, right, why I picked these people out of everyone in the world. Friends are the family you choose, right? I want to give a huge thank you to my friends Leah, James, and Catherine, who are right there in the audience. They're some of my oldest friends who are in person here from Princeton, California, and Ithaca, if you've ever been to there, which might as well be in California. And they have spent this whole weekend with me. They ironed my outfit before coming here, and drove me here, and just made it really easy to not think about this hour. I think each of us has a limited amount of time in this world, and every decision you make with that time is a choice. It's not lost to me, you guys, that you chose to use a lot of that time to come support me today. I remember last year I told Leah, that's the one who's switching my face, the first friend I ever made at Caltech, that I'd be defending this spring. And her response was simple. It was, just tell me when it is, and I'll be there. I also want to thank Tombi Gupta, who has had to hear more about the N-body problem, spin orbit resonances, and puppy planets than any human being should ever have to endure. I really hope you know how much it meant to me. And a very special shout out to my best friend Winston. You know, people are unpredictable and fickle, but you can always count on your stuffed sheep best friend to be there for you. I've seen some pretty cool and exotic places over these past 5 years. I've been to New Zealand, I've been to Leiden, I've been to sunny Pasadena, and Winston has been a comforting and solid presence at every single one of them. So not much phases this guy. Yeah, so thanks, buddy. None of it was possible without you. I'm really good at recognizing my friends, but to be honest, I think a weakness of mine has always been recognizing my family for the role that they've played. And I realized this recently, and I have introspected a bit on why. And I think it's really easy for me to take my family for granted because they've always been so unconditionally and omnipresently supportive in every single aspect of my life. And when that's there for long enough, you just forget it's there, right? And it's normal. But it's not, right? And I've realized that. And my family might not be down in the trenches with me every day or guiding the direction of my PhD, like many amazing mentors out there. But they've given me something even more valuable. They have given me the support to fail 1,000 times in the pursuit of my dreams. And I failed a lot these past 5 years. But I know that I could have failed 1,000 more times, and that support would not have wavered one bit. So I don't take that for granted. Not anymore, Thank you for everything. Now, I think every single person in this room probably knows where I'm off to next. But if you'll humor me, I still want a dramatic reveal. So, if we could get a drum roll, please. This summer I'll be starting as a Flatiron Research Fellow at the Center for Computational Astrophysics in New York City. Tiggy Wiggy, in the big city. You can imagine this. It's kind of a dream job, and honestly, it still doesn't feel real. I remember when we first moved into our offices 3 years ago, everyone had a desk whiteboard that they could write to-do lists on, right? Like write silly things, like finish this paper, make this fun. I thought that was really stupid, so I wrote Forbes 30 under 30 and published 20 papers on that whiteboard. And one of the things I wrote on that board was accept CCA postdoc because it really seemed like such a pipe dream at the time. I want to thank all the wonderful people at the CCA for their hospitality and all their kindness in my many visits there, I'll never turn down an opportunity for that kombucha on tap. And I was really lucky. I was really lucky to receive a few appealing offers this cycle, and it was by no means an easy decision to accept this one here. But having spent some time there, it really feels like the right choice. I want to especially thank Jai Dong, who's been my main point person for all my CCA-related questions, and he's been so helpful and so patient and so encouraging during the application and the decision-making process. I know I'm joining an incredibly vibrant and friendly community next year, and life changes are always scary, but it's not dread here. It's nervous excitement. I'm really excited to see what the next steps are. There's last but not least, there's one more person that I'm really grateful for. And that's this guy. Right? Because as much as I love, cherish, and appreciate all the people that I have spent the last 24 slides talking about, none of them are defending their thesis. Right? So if you'll humor this budding new doctor, I'm going to talk about me for a little bit. It's my thesis defense. What are you guys going to do? I know when you look at me, you see this flawless human being who has it all figured out. It might surprise you then to know it wasn't always this way. I was a late bloomer. The first years were tough. This isn't a normal job, You wake up on Sundays to do your work, not because you have to, not because your advisor is dropping by your house with a shotgun, but because there's nothing you'd rather do, right? So when someone tells you that's not enough, after you put your heart and soul into an exam or an application, it doesn't feel like your work's not enough. It feels like they're telling you your life's not enough. I'm not saying that's how it is, how it should be, but that's just how it is. And I do distinctly remember during one of the lows of my infamous floundering phase, I ran into Briley Lewis by complete random chance. We just happened to be visiting UC Santa Barbara together. And we had this conversation, and honestly, I'd be shocked if she still remembers it, because to her, it must have seemed like such an off-the-cuff, small, casual thing, right? But just like a little bit of puffiness in your planet's atmosphere can save you from tidal disruption, you'd be shocked at the effect that these small, inconsequential words can have. And Briley told me, who was already this superstar who had been awarded the prestigious NSF postdoc fellowship, she told me that when she was where I was, that she was also floundering. And I remember this like it was yesterday, actually. I remember she told me this. She told me that my competence was going to be exponential. And after that, every time I doubt myself, I would think about that. And today, looking back at the journey, I'm just really, really proud of myself for sticking with it. And maybe someone here needs to hear that, right? Because, I'm not saying it's going to work out. There's some survivorship bias there, right? But I did make it in the end, right? By all the objective and external metrics, it worked out. And maybe someone here needs to hear that not long ago at all, I also felt lost and helpless and confused. Sometimes it works out. And I couldn't have done it without all the amazing people in my life that I spent the last 25 slides talking about. But I've always firmly believed that it's possible to feel two things at once. So I'm really proud of me too. And I, for one, am very I want to end on this idea of radical optimism. It started as a joke or a coping mechanism between me and Consti here during postdoc season. We were doom spiraling about jobs, and we decided no more of this. We were going to be radically optimistic. We were going to get all the jobs, and the sun was going to always shine, and we were going to live happily ever after. But what started as a joke has become a lot more meaningful to me. It doesn't mean toxic positivity. It doesn't mean just put a smile on your face, squash all the negative emotions, and ignore the enormity of the tasks at hand, because I hate that idea. No, I think my advisor, Milena Rice, put this really beautifully in a speech she recently gave.
It is a radical choice indeed to remain optimistic, kind, and unyielding in times of turbulence, uncertainty, and difficulty.
Grad school, and a lot more importantly, life is emotionally abusive, and you'll have so many chances to check out, to become bitter, cynical, closed off. It's a choice you make every day to not do that, right? It's a choice you make to stand firm against all the turbulence that the world can throw against you, stand against it with hope for the future, compassion and empathy for the people you love, and radical optimism for your own life. I'm not saying that's an easy choice at all, right? Honestly, it's on the contrary, it's the hardest choice you can make. And I'm really proud to say that through it all, I'm still the same Tiger who's slightly cringe and loves his friends more than anything in the world, and is still excited to do science for all the right reasons. Maybe it's a little presumptuous of me to give advice to a lot of the people in this room, but it's my thesis defense, so what are you gonna do? So this is my advice, right? Slide down the obstacles head first. Put your heart on the chopping block. Love your science, love your friends, always cite the homies. Commit unapologetically to the pursuit of your hopes and dreams. It's scary. It's really terrifying. You're gonna get hurt. A lot. Now, sometimes to your very core, but I really believe it's worth it. As a PhD student, this is the day that you think about for 5 years, right? This is the day that all of it, the ups and downs, the hopes and dreams, the laughs and tears, this is the day that it all points to. For me, today has been perfect. So thank you all so much for being a part of it. And yeah, please hit me with some tough questions now.
Am I supposed to ask a question?
I've actually never done this
That's
before.
part of my job. Any questions? Chris?
I feel like it's crazy for anyone to ask a science question. This beautiful pouring out of amazing thank yous, but I do want to ask you something. I saw in your equation the tidal precession, the dependence on the star's radius. How do you know the radius of the star how do you know the radius of T11?
That took a while. Right?
Or does it not matter because MB over M star is so small?
That's true. That is smaller, right? I still think the radius of the star matters, right? This is the very first step into this, right? We only consider the change of the radius, right? There's a lot of other structure quantities in here. Love number, for example. Mass might change, right? Radius of the star. This is certainly not, the correct evolution of the system, right? We made a lot of simplifying assumptions. This is just kind of the simplest proof of concept that structure evolution is important to the dynamics. I see a lot of comments on the Zoom. Is there anything?
They're all just really congratulating you a lot. There's no questions yet, just a lot of congrats. They're very proud.
What, according to you, is the coolest thing you've learned about astronomy in these 5 years?
Oh, this is great.
Absolutely not that.
Funny time?
Yeah, funny time. Remember when I said that tidal heating heats up the interior of the planet, and that puffs up the planet's atmosphere? An open question is actually, where is that heat generated, right? It's not clear. Is it, at the core? Is it uniformly through the atmosphere? We put it in the core because that's kind of the most optimistic place to put it. That's the place that the atmosphere puffs up the most on, right? But no one knows. I've asked some of the most brilliant internal structure modelers in the world, and they have no idea where the tidal heating is deposited, right? And the reason it's so difficult to know that is because planets are beautifully complex things, right? Like, the answer for Earth is that there's this bay in Canada where all the tidal dissipation, or all the tidal heating goes, right? Not all of it.
It's like 1%. 1% is a lot.
Did you have to ruin that?
1% is a lot.
It's a lot. It is a lot. She's a professor of astronomy. Yeah, and it's crazy, right? Because the reason that all the dissipation is there is because the size of the bay, right, is just the perfect size to match the frequency of the moon, right? So, like, until we know about exoplanets to that level of detail, right, it's tough to say where it's deposited. We're just going to put it in the core. But I think it's pretty cool that, like, some random bay in Canada gets 1% of the Earth's tidal heating. Well,
Someone, my committee member actually asked me this. So, after 5 years, you could consider yourself a world expert. You know all these things about dynamics and coding. If you could go back 5 years and just do it all over again, what's one thing you would change to do that?
these questions are harder than the ones you guys asked me in my class.
We questioned you for like 3 hours.
I'm not saying they're easy, but that was really hard. Could I say work with Milena earlier?
Yeah, you definitely can. I'll just let Greg know, so he'll.
No, I mean, I just don't think so, honestly. Like, I think I did a lot of things wrong, right? There was a lot of, difficulty and a lot of ups and downs, but I think it all brought me to this day here. So yeah, I don't know if I would do anything differently.
Chris,
What
another science
animal
question.
is Winston?
I said
She's a
she's a
sheep.
sheep. Yeah.
You were in the
I thought it was a
I said it was just a sheep.
Any last questions? Otherwise, we can thank Dr. Liu. And I believe there is cake and champagne to celebrate in the back. And then don't forget about bar. We'll be heading there sometime, whenever Tiger goes there. Is when we'll go. All right.
Yeah,
Thanks,
thank you,
everyone.